All right, I think we can get started. Welcome to the L2 Interop working group. This is call number 19 in the series, and it is issue 1899 in the PM repo for anyone watching the recording. Cool. We can kick things off. I've dropped the agenda in the chat, also in the Telegram group. The agenda has shifted a little bit. We will start off with an update on the on-chain registry for chain IDs using on.eth. We have the Unruggable team and Thomas whenever you are ready.
Perfect, thank you. I've just request screen sharing if that's possible.
Yeah, try one more time now.
Uh, um, okay, perfect. Is that working? Can everyone see that?
Perfect.
Perfect. Yeah, I'm Tom from Unruggable. We're ENS service providers, and we've been working with the team at Wonderland and Josh and Barnaby at the EF on this chain registry resolver and the associated specifications 7930 for the binary interoperable address and 7828 for a more human readable form. This update is, I'll keep it brief. We have momentum at the moment. Things are moving forward. There's been a lot of conversations going on behind the scenes, and finally, it looks like this is all coming together. So the chain resolver code is complete and finalized. I can share a link to that on the chat. I'll do that afterwards. If I change my tabs, I'm assuming that people can see the changes as well. The executable proposal to register the on.eth ENS name and to set the resolver to the on-chain registry resolver is in motion. So I'm hoping that within the next 24 hours or so, we will have that up for an executable proposal. The timelines for those are 7 days, essentially. And there has been complete support from the ENS community. So I don't anticipate there being any issues in terms of getting that passed. I will additionally share that link such that if anyone wants to join the ENS forum and share their insights and opinions, please do so. There is also a companion associated post on the related specs on ETH Magicians. Again, I will get that link and share that if anyone wants to comment there. In addition to that, we've been to get to this point, we have set up an experimental registry resolver on mainnet on cid.eth, and we've been playing around with that and testing that that is fully functional, and the few issues that we did encounter have obviously been fixed, and now everything is in a good state, hence why we're moving this forward to the productionized setup on the on.eth second level domain. So if people want to just have a play around with the fun little additional user interface that we set up, you can visit cid.eth.limo and you can have a play. That pulls data from that experimental registry and displays it in line. And that is simply a friendly user interface to allow people to visualize what is contained within that registry. In practice, we anticipate that people will be using the registry for chain specific address resolution. So that's example.eth at base, whereby that base label gets resolved to 7930 interoperable address, which is this binary address here. And then you can utilize that to resolve the ENS name, which is the first portion of that address. Because it's been queried a few times, some points of note in terms of how we architected that registry. There will also be aliases. So if there are multiple labels by which a chain is represented, OP and optimism, for example, they will all point to the same canonical underlying metadata. We are still in the process and conversing about exactly the process behind how we're going to allocate these names. But the kind of anticipated plan is a multi-sig made up of industry participants, um, probably people from the EF, people from ENS. And if you are interested, we're open to kind of having that conversation and making sure that kind of everyone's needs are met in that regard, because I appreciate that if people are relying on this for their chain metadata, it needs to be appropriately secured. I imagine that Orca from Wonderland is on the call. We've been working closely with them and they've been doing fantastic work as well. I think he's talking about open intents after this, but I'll briefly mention is interopaddress.com, which is a website that they've set up that looks super cool and additionally provides a lot of kind of context and insight into how this works. But this animation at the top, vitalik.eth at, followed by the chain label, which will resolve the metadata from that chain registry, is particularly cool to me. And Orca recently told me that their SDK, which is linked from here, now has experimental support for that experimental chain registry. So if you want to kind of begin integrating this into your products, you can now kind of play around with that experimental registry by setting a flag. And in 7 days or so, we'll be in a position to add the functionality to use the real productionized on-chain registry. Another question that I've been asked, the on-chain registry is a registry for all metadata related to a blockchain. The intention is that ownership would be handed over to control the metadata associated with a particular chain identifier to the multi-sig or equivalent associated with that chain operator. Again, we're working on defining the process to make sure that we actually do hand off that ownership to the correct people and teams. But ultimately, as well as the 7930 identifier, which we're pushing as hopefully the future way of kind of representing chain-specific addresses, this registry resolver will be able to be utilized to share any and all metadata associated with a chain. So this is the experimental registry, which just has some example data to demonstrate that. That was quite quick. I'm happy to answer any questions, and I will share any links that I just outlined on the chat.
Thanks so much. Any questions for Tom? Super clear, no questions.
I guess I have a question. So, Thomas, I saw the interopaddress.com Wonderland site and I think it's really interesting. I like that little demo showing you could put jamespec.eth and put chain base, and then it shows you what the interoperable name format is. Help me just understand next steps for this to be something that everyday Ethereum users can take advantage of. Is it required that people, wallet companies implement the Interop SDK? Is this something that the Ethereum Foundation, Josh, is like really pushing as a wallet standard? Oftentimes, ENS is only as powerful as its implementation, and not all wallets are implementing ENS the same way. So I'm curious kind of like how this goes from research to idea to now executable to then actually useful for people.
Yeah, absolutely. I'm sure that Josh and Orca can potentially add context from their side. But in terms of my side and obviously your side, coming from ENS, I think ultimately with specification development and the tooling that supports those specifications, yeah, getting a specification complete and signed off and merged in is the first step of the puzzle, and then getting people to want to use it is the next stage. And in many respects, that's why kind of this has taken longer than we originally anticipated, because ourselves and the Wonderland team and the team at the EF have been debating and discussing exactly how we can kind of format these specs so they're accessible whilst also being useful to the widest audience possible. Ultimately, we think that we've got there, and we've been conversing with the people that will be utilizing this, and if there's anyone considering utilizing this, we're happy to kind of converse with them and discuss implementation. But at the end of the day, yeah, it does come down to wallet teams and DApp teams implementing these specifications and taking advantage of the on-chain registry resolver. And in that regard, I spent the past week writing up kind of some fairly complete and thorough documentation for all of its functionality, and we're hopeful that kind of by providing really in-depth specifications and documentation, and additionally supporting with integrations, hopefully kind of the pitch sells itself and people will want to, and then it will just grow naturally, we're hoping.
Yeah, Prem?
Yes, I just wanted to say it was good to see you last week, Josh. We were in Malaysia together at the L2 Feb 2 event, and I was able to have a conversation or a presentation of 7930, 7828, and the on-chain registry. And I'd generally say that the feedback was very positive. I think from the ZK Sync, they said, just ship, and they were very supportive, and there were some other L2s there as well that were supportive. So I'd say that the feedback is good, and the idea at this point that I've talked to Josh about is the idea that we just need to ship, and we have a kind of a short window, I think, to get the most bang for our buck in getting the news out. So if we can all coordinate, work together, I think it would be great to ship something and see how far this project can go, and hopefully it can be successful if we all work together.
Awesome. Cool. And yeah, anyone, feel free, please, to, I think Thomas and Prem and myself would love to hear from more people. So yes, please reach out. Cool. Let's keep going then. Thank you. Yeah, thank you, Thomas. Next up on the agenda, we have Palace here to share some work they have underway on 7702, combining 7702 and 5792 to execute multi-step cross-chain actions.
Hey guys, I'll request screen share here.
Okay, there you go.
All right, so we have a light paper, and if anyone is curious to dive into more of the technicals here, feel free to reach out to me on Telegram. You can scroll up a bit. I'm in the Interop group, but I'll just briefly present the deck to give you an overview of what we've been working on here at Effortless. Just confirming everyone can see my screen still.
Yeah, we can.
Okay. So what we're looking to tackle is the high friction UX for cross L2, L1 to L2 user experience for retail users, specifically for new users who are not as familiar and haven't been as involved with crypto over the years. So we had an example flow, someone searching for how to bridge to base on Google and how they would actually get there. And we're looking to reduce that friction drastically so that while maintaining self custody and trustlessness, so that decentralized self custody can compete on UX with the centralized solutions that are coming out for cross-chain experience for retail users. The way that we do this, and here you can see that we allow complex multi-step actions and with single-click approvals. That is the goal here, and the way we do that is leveraging 7702 and then also 5792 to make it user friendly, to allow existing wallets, also applications that want to build on top of this standard, or any cross-chain aggregators, to be able to provide an experience to users with their existing EOA wallets that users currently use, that is more in line with the experience that centralized providers are now providing retail users, which are starting to see adoption. So we're using the two EIPs to allow these users to execute complex multi-step actions. So you can bridge to an L2 and then do a swap, or bridge to an L2, do a swap, and then put it into a staking contract or a lending contract, all in a single transaction. We ourselves will be building a product on top of this for retail in order to leverage the technology, but we also wanted to provide it as basically an open standard that is separate from the monetized product that anyone can use to improve the decentralized, trustless self-custody experience. The architecture we're using, in addition to EIP 7702 and 5792, is we are going to have an L2 for purely record keeping. So the L2 that we are going to have is not intended to have anything on it outside of record keeping of cross-chain transactions, so that there is a proof in one place outside of the various chains involved or L2s involved. And then we believe this is going to support various applications on top of it, various use cases on top of it. We will be building on top of it ourselves. But yeah, that's the introduction. We are going to be using solvers to optimize certain parts of transactions, and using array of intents for other parts of transactions. We've been working with Benarbe and also spoke with Alex a bit on this, and yeah, we'll be sourcing feedback as we build this out. We're currently working on the architecture to make sure it makes the most sense in terms of how we are creating the logic for building out these transactions. But we want to, create an experience where retail users can express in layman terms what they want, potentially in our product, to an AI agent, and that AI agent will create a complex transaction for them where they need to usually do one signature and then are able to execute that transaction themselves from their self-custody wallet, rather than transferring their funds to a third-party smart wallet or a third-party AI agent where the agent is managing their money. In this solution, they will completely maintain self-custody. yeah, so that's what we're working on. If you're interested in learning more, feel free to reach out. We would love to, walk you through what we're building more in depth and get feedback and um, see if this makes the most sense for who we're building it for. Our plans is not to make this protocol competitive with any existing L2, any existing wallets, or applications, so that it's a value add to the ecosystem that other applications can build on top of. Wallets can potentially integrate for their users, etc. And happy to answer any questions if anyone has any here.
Any questions for Palace?
I added one in the chat. I asked about will the L2 act like as a mempool?
So the L2 will act purely for record keeping. So we have a atomic intent protocol, which is where the solvers will bid for a transaction and try to provide the most efficient path to solving the transaction. So that would be separate from VL2, which is purely for record keeping the various transactions, the confirmations as they happen on the various chains.
So I still don't quite understand. So is the L2 kind of used for like the settlement of the intents?
Uh, the L2 is used as a place where all of the various confirmations of transactions on the various L2s is um, like kept so that because there's going to be the confirmations of a transaction on Ethereum, on Base, or whatever L2, and those are all in different places. And so the L2 seeks to be a place to represent all of those, so that it tracks the finality across the various chains. And so um, that's what in one place, you know.
I see. So it's like you're kind of like mirroring the transactions on all of these other L2s to the effortless L2.
Yes. Yeah. So it's a pretty simple purpose chain. It's purely for record keeping. Yeah. Thank you guys for letting me present here.
Awesome. Yeah. Thank you, Palace, for coming on. Cool. And anyone, reach out on Telegram to Palace. Cool. Up next, we have a quick round of updates on the Open Intents framework from Orca and the Wonderland team. Orca?
Hello. Yeah, let me share. Firstly, can you see this guy?
Yes.
Perfect. So let me see. Slide this. Perfect. So quick update, I guess, on the IF. I guess it goes without saying, the OF is a collective work from many, many teams. I think there are lots here. I guess I'd specifically call out Open Zeppelin, Li-Fi, and Uniswap for some of this recent work, as well as, of course, the EF. But lots of people have been involved, and I'm mainly just presenting the collective effort. That being said, the Open Intents framework, I will quick overview. So it's a full stack framework for intent-based cross-chain interop, focused obviously on L2s. The idea is to bring intents to all of Ethereum as a best-in-class technology stack and an open source public good. What does that actually mean? It means making it really simple to set up intents on a chain and to run ongoing operations. We want to avoid vendor lock-in. Want to have this open interfaces where folks aren't having to pick one particular vendor. Overall, want to reduce fragmentation and deepen liquidity, while giving people modular settlement options. And in particular, we want to highlight trust minimized options as well. So there's quite a lot going on there, and I guess we want to go into what that means in practice. And I guess there's a mixture between sort of standards and specifications and useful software. So just to orient, and this isn't a description of every type of OIF flow, but it's certainly indicative. You start on the left with the user, they'll request a quote. Those quotes will go to solvers who will return quotes. The best quote will be selected. That's intent will be submitted, and then the solver will fill that quote, and then they'll prove that they've done what they were required to do. That proof will be validated, and the assets will be released. And that essentially is the full sort of life cycle of an intent. From a user perspective, it's quite interesting. Obviously, they're mostly just interested in submitting their intent and then getting their output assets. But there's obviously all this other stuff that happens under the hood that lots of people here will be aware of. So I thought it'd be interesting just to break down the different parts and progress across this flow. So starting with, I guess, with the ERC-7683. So this is an interface, a standardized interface for cross-chain trade execution systems. And people will be familiar, I guess, with the standardized event, which was initially defined. And people may not be aware of the recent, or actually quite ongoing effort to essentially revisit this standard to move away from standardized events, and you can look into the details of why that wasn't the best fit, to standardized on-chain resolvers. And so this essentially takes a standard which caught the popular imagination or collective imagination quite a lot, but which hasn't gained the traction that we might have hoped. So I'd encourage people to review the ETH Magicians post and provide feedback and engage with that, because we think that it's a new pattern. This resolver-based pattern is a great way for lots of protocols to be supported in a way that the event-based approach didn't manage to accomplish. So that's essentially the representation part of the flow. We've then got this big chunk over here, which is the OIF contracts. So this is an open source repository. So these are modular smart contracts for intent settlement, consisting of settlers and oracles, essentially managing all of this part, which says, okay, was the intent filled? Did they do what they said they were going to do? And repaying the solvers. And so these contracts have been audited and they're ready for use. This was worked on by OpenZeppelin through a large part of last year. And these are largely good to go. There's still opportunities to add additional types of oracles, and there's still some iteration in terms of making these support more, like essentially more things, maybe multiple inputs, multiple outputs. But the contracts are good to go. The broadcaster is one specific contract which is underway at the moment, or being worked on at the moment. So this is a reference implementation for ERC-7888, which is essentially a storage proof based way to pass messages from one chain to another, where they share common ancestors. So this is really the rollup, like in the rollup context. And this is a callback that we want oracles, and we want ideally to have trust minimized oracles. So the broadcaster is a trust minimized option. And these contracts are currently being audited. Again, this work by the OpenZeppelin team. Next steps for this would be integrating the broadcaster into the OIF deployment process, so new networks don't need to depend on any external oracles to get started with the OIF. The OIF specs, so again, coming up here, this is at the other end of the life cycle. So this is essentially standardizing the interface between the user when they're requesting a quote, and then also when they're maybe broadcasting a quote if they're doing that off chain. So again, this is an open repository which standardized quote and quoting, intent submission, and asset discovery. We're currently implementing these both on the client side and on the solver side, which we'll see in a second, and we're testing and hardening them for robustness and usability. We'd encourage more and more folks to review the specs. So if you're an Interop provider, be interested in your take, particularly to weigh in on some recent changes. So we've moved away from some of the binary representations that Thomas mentioned, so the 7930, to the more human legible text identifiers at the API level, rather than the smart contracts are still 7930 addresses. But again, this is based on feedback that it was quite hard to integrate, when you didn't have slightly readable essentially addresses and chain identifiers. So we'd encourage folks who are interested in this part of the life cycle to take a look and familiarize themselves. Finally, or not quite finally, but the solver. So this is essentially the reference implementation of the OIF specs, and it's also an out-of-the-box solver that can be used to provide intent-based liquidity. This is available for testing. It's on Arbitrum based and OP with mock USDC tokens. And OpenZeppelin are also working on a user-friendly onboarding flow for L2s to set up an OIF solver for their network. So that's the current priority. So essentially making it work out the box with minimal configuration. Obviously, people could run solvers today, but this is trying to make things more user-friendly. And finally, we come to the user end of the spectrum, which is the Interop SDK. So this is an interoperability toolkit for wallet and app developers. Thomas mentioned the addresses module, so this supports interoperable addresses, but here we're most interested in the cross-chain module, which essentially implements the OIF specs interface, allows you to interact with OIF compliant protocols and also some others. We're really interested now that we've got like the initial functionality in place to talk to wallet apps and other teams interested in adding cross-chain capabilities. So this is, and we'll also be releasing some demos and the initial version and documentation of this imminently. And so that was a whistle-stop tour. There was quite a lot there. Overall, we're at a point where we've got a lot of really great stuff. We want to talk to people, whether those are L2s and rollups as service providers, in terms of getting the OIF up and running on your chains. Solvers, we're interested in talking to them about getting started with filling OIF intents and starting to think about these interfaces and how to integrate with, whether it's at the 7683 level or at the API interface level. Interop protocols and infra providers, how to leverage the OIF, how to think about it. We're obviously interested in folks maybe applying or building in line with the specs, but also just interested in having discussions about how the OIF can fit in. And then, as I said, wallets and apps, we're interested in talking to people who might integrate the OIF or other interop providers just to understand your pain points. So I know lots of those kinds of people on the call today. And so, yeah, encourage you to reach out. We're all in the Telegram is probably the best place to start.
Thanks so much, Orca. Do you want to, take Ellie's question on the difference between 7888 and the cross-chain broadcaster?
So I think Arbitrum's cross-chain broadcaster. I know that the Arbitrum team were working a lot on this initial broadcaster. I actually don't know the difference between that, but I can follow up with the Open Zeppelin team. I do know that the Arbitrum team have been providing a lot of feedback on the broadcaster design. So I don't know if any of them are here.
Yeah, I don't see them here. But yes, we should we can ask one of them to chime into the Telegram group.
And in terms of the Telegram group, it's the L2 Interop. What's the title of it, Josh? It's the
Okay, just the base group.
yeah. I think
Okay.
when we can fork off as required. Cool.
Awesome. Thank you, Orca.
Thanks so much.
Alrighty. Next up, we have Jordy, I believe, here to share some of his latest work and research on.
Explain a little bit the proposal that I met in the ETH research. So the idea is about how I see the inter-rollup composability, especially the synchronous composability. First of all, I'm very quick. I mean, this idea of separating data and proofs. I mean, the idea is, and if you have all the transactions, imagine not just the transaction of an L1 or you a transaction of an L2, that's the only thing you need. The idea is that you can have the data, you can have queries. These queries generate the proof, and you can have the state. I mean, the query maybe is the result of a state, but just having all the data is enough to reconstruct the state and proving that that state is correct. Okay. In the idea of when you have multiple rollups, let's forget about the layer one for a moment. When you have multiple rollups, the idea is that you can have very easily cross rollup composability. The idea is that you put all the transactions in data availability, and this by itself it gives it already, you can already do calls between one roll up and the other. I mean, it's synchronous calls. For me, when I'm talking about synchronous calls, is making a call. I mean, the idea is that you should be able from one roll up to do a call. I mean, an EVM call to a roll up that's in another EVM, and the other way around. And a call in roll up two, then should call to roll up one, or even to layer one. Okay, so this is the, I mean, this is the idea of the concept. So for when you have only rollups, then that's quite easy. I mean, you just put data there. These transactions can talk one each other, and you just generate the proof that actually aggregates all these rollups. Okay, but in the interesting part, the interesting part is when you go from L1 to L2 composability, and this the idea of the proposal is that without even forking L1, you should be able to, from L1, to call rollups on layer 2s, and even from layer 2s, call rollups on layer 1, even without having to redeploy. I mean, keeping all so having to redeploy the contracts in L1. I mean, they just, I mean, if you want to do an Uniswap exchange from an L2, you just call to L1 and you just do the swap, like if you were in the same L1. Okay, so how we do that? And let's go to deep a little bit. Well, the first thing is this idea of address. I mean, when proxy addresses. I mean, when you are doing a call, if you are doing a call, how you say that you are calling to a rollup 2. I mean, you can do a specific interface for that, but then you would lose compatibility with that. So the idea that we propose here is to work with what we call proxy rollups. I mean, these proxy rollups are, well, just are special smart contracts. That's how they emulate what you would do in the other rollup, and these proxies are create two rollups. I mean, are counterfactual contracts that are already representing this. Okay, so in this example, for example, when we have a user, okay, a user is calling to a DAO, and the DAO maybe is checking in L1 again if it's in a whitelist or not, and then it allows you to vote or not. Okay, so it's a double call. I mean, you are calling from L1 to an L2 and from L2 to L1. Okay, well, the idea is that the user would call to this proxy contract, okay, and this proxy contract would do the call. This proxy contract will do the call to the whitelist, and then will return the result to here. Okay, so you don't have to cross the L2, because this proxy would emulate what you would do actually is executing that. Okay, and how we do that? Well, the idea, I mean, the main idea is building what we call this execution list. Okay, so the idea is execution list is okay. So the idea what we say is in this, what happened if in rollup 1 I'm in this state and I execute a call to a vote? Well, then you go to this state, okay? And in this case, the result, it would not be, it could be a return, okay? So the result is this, but in this case, it's just another call that happened in L1, okay? We have another execution is what happened if in L1 actually I'm returning, so I'm going from the alt state in L1, I'm returning from the whitelist, I'm returning whatever that is, this is true. And well, what happened is that the rollup will go to this new state and then will return the vote to 1 to true. So the idea is that, of course, this table can be in the storage and can be put beforehand by the sequencer. And then the idea how it works. Well, the idea is that when you are doing this call to this proxy call, actually instead of, so in order to execute, what you do is you look in this execution table what happened, you update the state. So this execution table actually you update the state on the rollup too. So this is updating this state means that this execution actually happened, and you emulate a return back to here. Okay, but the idea is that I mean the cool thing of this is that from the layer 1 you just see normal calls. Okay, the only thing is that they are to this proxy or from this proxy. Okay, but even if you have nested calls, L1, L2, L2, L1, L1, L2, or even with rollbacks or so, you can emulate exactly the same things. When you do a rollback, then you can do you execute that with a nested place, and then you remove from I mean, you can do a rollback also in the L1. So The idea of this at the end is that you are very much working with many rollups. It's like if you were in the same space as if you were in the layer one. Okay, and the good thing of this is that you don't need to do any fork. And the other thing is that rollups, they don't need to be even EVM. Of course, they can be EVM and they can be a standard and fixed, and there can be like native rollups, but you can. It's easily you can define your own rollup. It's good enough to have your own rollup. The only thing is that the rollup, the state transition function that you define, should be able to accept or make calls on that. Okay, so I think this is quite flexible. I mean, maybe you can go to you have some links. We have some links, some references links. They are all them in the research, but you can check there. We made a demo. I don't know if Martin is here. We did a demo of how this would work. So Martin, I just pass you if you want.
Sure. I'm happy to try to make this more, hopefully even more concrete. Let me try to share my screen. I have also a recording. So in case my demo fails, I'll share the link of the recording. But you can see my screen? Yes, right?
Yes.
Okay, so here is the roll up, and on the roll up there is a very simple contract, this counter contract that just has that you can call it with get, and if you call it with get, it will return the current value, but it will also increase the counter by 1. But I'm just copying here the address. And what I want to demonstrate now here is the concept that Jordi just mentioned. So I am now on the layer 1. In this case, it's actually a live deployment on Gnosis. Let's see if it works. And I just copy in this target address. And now I specify that this target is not an address, well, on Gnosis in this case, on the layer 1, but instead it's a target address on the layer 2. And if I do this, I get this proxy address, and this is deterministic. And now I can call this proxy address, and let's see if this works. And that proxy address should return the current. I mean, basically what this other contract on the layer 2 would return in a synchronous call. And of course, that is only possible by a builder anticipating this call. Yeah, let me just show it to you. So this is a simple contract that just allows me to do a call to a target address, and I'm using now this proxy address with call data, and this is just the encoding for the get function. And let me do this. So this is now a real transaction on Gnosis chain from my regular from regular EOA to first to this logger contract, and from this logger then to this proxy contract. And let's see. I will look here at the command line, and there's a builder running. So yeah, I should also say this transaction is now sent to the builder and not to the general Gnosis mempool, because now the builder should detect that this transaction is touching such a proxy contract, so essentially a contract on the layer 2. And now the builder needs to prepare the layer 1 by registering this call, what Jordi calls this. Jordi, what was your name again? This lookup.
It's execution table. I mean, it's proven.
Execution table, exactly. So let's see if that happened. Yes, so it did happen. So 44 seconds ago, this builder prepared this this proxy contract by doing register incoming call, where it basically told this, or where it basically prepared the this rollup contract in a way that it said, or that the proxy contract could now look up the result of this call in this registry. Let's see, decode. So here it basically says, if the L2 is in this specific state and then this specific call comes, then this call will return in that specific value. And what we should see now is that first the logger here, right? So call 5 previously did nothing, and yes, here it got the return and it locked this return. And we should see furthermore that that this counter, right, exactly. So this counter is now let me see. Right. So here we see exactly. So this is the call. Yeah, that now increased the counter one more on the layer 2, but also immediately synchronously got this result of the call available in the layer 1. So stop sharing. I saw one question. So yeah, circ. Yeah, I think it's. Okay, yeah, no, maybe I just pause here and yeah, also Jody, and happy to answer questions or comments or.
Any other questions for Martin or Jordy? Cool. Well, thank you.
Super cool, guys.
It's important to mention that all this is possible. Thank you to real-time proving. Actually, the what enables this is being able to generate proofs in very, very, very low latency.
Right. I should say, so the demo you just saw had no real-time proving. That was mocked. It was but yeah, I mean, but yeah, we know it is possible to generate those real-time proofs. So yeah, it's so I think our thinking now was really about how can we provide the synchronous composability as backwards compatible as possible, so that existing contracts that don't that basically just know a to address and it doesn't have a chain identifier, for example, that it still works with existing contracts that just have a to address, and therefore we need this proxy design to essentially implicitly put the target chain into the regular address, and then we need this lookup table and all those things. Alan, please.
Yeah, I just wanted to ask if you guys have started to experiment with real-time proving, maybe even for smaller blocks, just as a benchmark, see how much it's going to cost, latency, stuff like that.
Yeah, in this, actually, we are proving real-time Ethereum blocks. Actually, the average time is about less than 7 seconds. We presented that in Argentina. We were at 16 GPUs. Currently, in the next version, it's going to be around 12 GPUs. But the cool thing is that this scales very well. And the main work that we are doing right now is try to pipeline the proving with the block generation. The idea is that even while you are building the block, you can start proving, so that the final latency is when you finish to build the block, until you had the proof available. And here, right now, we at this point could be maybe 4 or 5 seconds, but we believe that this can be below 1 2 seconds for sure. So that's where we are working on this. Real time, I mean, is lowering the latency so that we can pipeline two things. Okay, and also parallelize. The nice thing is that when you have rollups that they don't touch on each other, you can build out these proofs in parallel and then aggregate. Aggregation is quite fast. I mean, aggregating two proofs currently is around 80 milliseconds or something like that, which is what allows you to scale very well. I mean, still is a technology that's evolving. We are improving day by day. Yeah, we believe that, I mean, talking about 1 second, 2 seconds proving time, the latency time, this is doable with current state of the art on the KVMs.
Cool.
Of course, proving is, I mean, it's expensive, but it's not that expensive compared to a transaction fee. So it should be marginal, the cost of proving with the cost of the transaction fee.
So we have a few minutes left. I want to make sure we can get to the final presentation here. And thank you again, Jordi and Martin. Anshu and Nethermind team, do you want to jump in?
Yeah, I'll share my screen. Can you see my screen?
We can, yes.
Okay. So Jordi and Martin really simplified my life because they just gave a very good primer on synchronous composability. So I guess I can skip that part. So our solution is also focused on L1 to L2 synchronous composability. And today for this presentation, we would like to focus on one half of it, where if you are on L1, you can call any L2 contract and get a return call back to L1, exactly as if you're calling a contract on L1 itself. So let's say for this demonstration, I would like to show you a cross-chain DEX, wherein you have liquidity on L2, and on L1s, you just have your input token, and you basically swap it using the L2 liquidity as if the entire liquidity was on L1 itself. So I'll give a quick demo and then I'll run you through the architecture of what's really happening internally. So let's say I want to swap ETH and I have ETH on L1, not on L2. At no point will the user himself touch the L2. So here I'm swapping ETH for USDC. And I have ETH on L1, the DEX is on L2. I'll get back USDC on L1 itself. So I click on swap. I sign this user op and I'll get back to what this user op is. Now this user op is basically being sent to a builder/sequencer who is now sequencing the transaction and the swap is done. And you can see I got my USDC back on L1 and this was pretty fast. Of course, the assumption is that I have real-time provings enabled. But yeah, right now it's just a mock proof. So what's really happening here? So this is based upon our same slot L1 to L2 message passing research that was published by Lynn from Nethermind about a year ago. So in this design, the builder/sequencer is essentially concerned about three separate transactions. Firstly, the L2 call transaction, which is a call to an L2 contract. And then the actual L2 block proposal. And this L2 block needs to have the L2 call transaction in it, plus this thing called hot L1 state. I'll get to what it is. And then eventually the L1 call transaction itself, which is like the return data that is passed from the L2 call transaction processing on the L2 state, basically. And the builder's primary job is to sequence these transactions correctly as a multi-call batch in this design. And of course, the builder also needs to put the correct hot L1 state within the L2 block proposal. And that's it from the perspective of the sequencer. Once they sequence these three transactions correctly as a multi-call batch, they push it into the L1, and that's it. You basically get this demo once you do that. But what's really happening internally? So starting with when I start the swap, this thing that I'm signing, this is a user op. Now we don't really have a particular standard that we are advocating for this user op. This could be like a safe wallet op, it could be an intent, or it could be any related ERC. It's completely agnostic of what this is. By default, a user op will obviously have like a target, a value, and of course some call data, and a smart wallet that executes it, or a smart account. So in this case, the user op simply sends or one of the tokens, depending upon which one they are swapping and the swap direction, over to an L1 handler contract. And this L1 handler contract starts talking to the L1 bridge. Now, we have not really made any modifications to the default L1 bridge that is offered in Tyco stack. And again, an important disclaimer here that we are using the default Tyco/Surge stack, and we are using that bridge, and we have not made any major modifications to that bridge. Rather, we have made this entire system as like a plugin for the existing bridge that Tyco-based rollup offers. So this L1 handler contract, it communicates with the L1 bridge, and it basically constructs the call data that enables the swap on the L2 state. Now for the user, it's nothing not the user, but more like the L1 contract. It's absolutely indifferent from just calling, let's say, as if the L2 handler contract was on L1 itself. So it passes in the token and some call data over to the bridge. And then the bridge communicates with the L2 bridge. The L1 bridge communicates with the L2 bridge. And it just continues the trail of passing the call data over to another handler contract, which then conducts the swap within Uniswap or whatever DEX we have deployed on the L2. And then the same trail repeats, but now on the L1 side. So the tokens are returned over to L1, then the L1 handler contract is called back again, and the tokens are finally returned to the smart wallet. Now, what's the caveat here? The caveat is this, the hot state. So what is exactly this hot state? So in the usual case, like asynchronous composability, when you are posting a block on L1, there's always a hot state. And this hot state is at best the state of the previous L1 block, right? This is the state that you can sync with the current L2 block. Because in EVM execution, you obviously don't have the state of the current block with you, right? You obviously have the state of the last block. So there is no way to get synchronous composability using the hot state or the hot EVM state, like the state root. But what we can do is we can get the hot state of a single EVM storage slot. And that is what we take the advantage of. So whenever this call data that we have here, whenever this is sent to the L1 bridge, we basically let's say hash it, and we store it in a certain EVM slot. And we basically get the state of that slot, right? And that won't be changing, irrespective of what happens to the rest of the EVM state. The state of this slot or the value of this EVM slot won't be changing because we have already set it via this internal transaction. And what the builder now needs to do is the builder needs to record this hot state and push it within the block that it's proposing. If some of you who are familiar with the Tyco stack, you might know that this is done via the anchor transaction, which is like a system transaction that has to be the first transaction in a block. So you can pass this hot state which is just a 32-byte hash in that anchor transaction itself. Now, once you pass this, all you need to do is just go ahead with your proposal. That's it. And automatically, these extra plugins that we have created on top of it, it checks that this hot state is matching the call data that you intend to execute, and it processes the L2 state accordingly. And that's it. And then once the L2 state has been processed, the only thing that the builder has to do is push the L1 call. So when the L2 processing is done, the L1 call that is initiated also has to be pushed in by the sequencer. The sequencer might as well, just not do this and ignore this. We don't really have a control on that. But then from the user's perspective, that's not a big issue. Yeah, it's a user experience issue, but the user can also manually sequence this transaction, because this entire process is completely permissionless. And at no point the builder has control over your funds, or can mess up your funds in any way. So yeah, that's the overall architecture that we have created here for synchronous composability.
Thanks so much, Anshu. We're a few minutes over, but any closing thoughts on your side or any quick questions before we end? Otherwise, we can.
Good night, demo. Thank you.
Cool. Awesome. Sorry, went a little bit over. Thanks everybody for joining. See you next time.
Thank you, everyone.
Bye-bye.